All right, guys, so we're going to continue on with growth and decay, and here we're going to talk about how to use exponential functions to model growth and decay in applied problems. So in many of the applications that we look at, the rate of change of a variable y, which we would actually write as dy dx, is proportional to, so that means equal to some number times the value of y. When y is a function of time, we can write that proportion as dy dt equals ky. Now, what we want to do is solve this equation to get the general solution for the exponential growth and decay model. So this is a candidate for separation of variables. So dy over y equals k dt. Okay, now there's no t in the equation originally. But when we anti-differentiate here, slap our integral symbols, k stands for a constant. So when we have dy over y, the solution is natural log absolute value of y equals, now k is a constant, so the antiderivative is going to be k times t because we're integrating with respect to t plus c. Now we want to solve this equation for y. We could exponentiate both sides. So you'd have absolute value of y equals e to the kt plus c. Now, let me just bring up a little bit of algebra for you. Do you remember if you had like a to the x times a to the y, that would be a to the x plus y? So that's like when you multiply like bases, you add the exponents. Well, in this case, um, we would do that backwards. So absolute value of y equals e to the kt times e to the c, because the kt plus c is being added in the exponent. So we could think reverse that product property for exponents. Since we're adding in the exponents, we can rewrite it as multiplying like bases. Now, e to the c is just a constant. So I'm going to write this as absolute value of y equals c e to the kt. Okay. Now, in most applied problems, y is going to be positive. And this is how we take care of the absolute value. Because if we take off the absolute value, y could have been positive or negative. So plus or minus ce to the kt. Now, if y is greater than 0, then you would have the exponential growth and decay model. Y equals ce to the kt. Now, it's going to be growth for k greater than 0 and decay if k is less than 0. Okay? So, in general, if you have a situation where the rate of change of a variable y is proportional to the value of y, so in other words, you have this differential equation, you know that its solution is going to be y equals ce to the kt. Okay, you don't have to go through this proof every single time of solving that differential equation if that's the situation. So let's look at an exact actual situation. The rate of change of y is proportional to y. So that is saying that dy dt is equal to kt. So we already know, we don't have to go through and prove it, that y equals ce to the kt. So when t equals 0, y equals 2, that gives us an initial point, 0, 2. And then t equals 2, y equals 4. We want to know what is the value of y when t equals 3. So notice that the y value is getting larger. So I know that this is going to be growth because y is getting larger as t increases. So I know that when I do the problem, k should be greater than 0. So since I have the initial condition 0, 2, I can plug that in. So 2 equals ce to the k times 0, which would be 0. E to the 0 is 1, so I know that c equals 2. So now I can further refine my equation to have y equals 2 e to the kt. Then I plug in my other point that I know, 2 comma 4, and this will help me solve for k. So I'm going to start here. Y equals c, which we found to be 2, e to the k times 2. Okay, now we want to solve for k. First thing we could do is divide the 2 off from both sides. So you'd have 2 equals e to the, I'm going to write that as 2k instead of k times 2. Natural log both sides. Then you would have natural log of 2 equals 2k. So k equals natural log of 2 all over 2. Now, if you plug that into a calculator to get the decimal value, um, just be careful that you do natural log of 2, close the parentheses, then divide by 2, because you don't want to put the 2 over 2 inside of the natural log. All right. So the value of k is going to be approximately 0.3466. So now we can write our equation. Y equals 2e to the 0.3466 t. This is our equation. And here is the graph of the situation. Notice we have our initial condition, our other point, and then we can use this formula or this equation to get the y value when t is 3. You just plug that into Desmos as is, but put 3 in for t. In other words, you could write 2e to the 0.3466 times 3. Okay, so I'll show you how to do that just so we're clear on what to do. So I brought up our Desmos with our equation in it. If I rename this f of t, then I can use function notation to evaluate it and do f of did we want? We wanted when t is 3. Okay. And then you can actually get any value you want there. All right. So that's just an easy way to do it on Desmos. If you type it in, you would just do 2e to the 0.3466 times 3. But see how the times 3 went down? It's not in the exponent anymore. So that just means I need to group the exponent in a parenthesis, and then that will take care of that issue for me there. So the next thing we want to talk about is radioactive decay. This is measured in terms of what we call half-life. And that's the number of years required for half of the present amount of radioactive material, whatever it is, to decay. All right. So like if the half-life was 10 years and you had 50 grams originally, after 10 years, there would be 25 grams left. So let's take an example. 10 grams of plutonium isotope 239Pu were released in a nuclear accident. How long will it take for the 10 grams to decay to 1 gram if its half-life is 24,100 years? Now, there's in our book there's like a little table with the half-lives of several different radioactive substances. So if you need to look any of those up. But in this one, we have the information that we need. So what we can do is start off knowing that radioactive decay uh, decays according to the exponential growth and decay model. So we know that y equals CE to the KT, but in this case, K should be 0 because it's decay. It should be less than 0. So I think negative is going to cause it to decrease, essentially. So when we solve for K, we know we should end up with a negative number. Okay, so 10 grams were initially released at the accident. That tells us the point 0, comma 10. We also know that its half-life is 24,100 years. So after 24,100 years, you'll have half of it left, which they didn't tell us what that amount is, but they kind of did because if there's 10 grams initially, half of that would be 5. So if we plug 0 into this equation, set it equal to 10. So we have C equals to 10 equals CE to the 0 power, e to the 0 is 1. So that lets us know that c equals 10. Okay, so we have y equals 10 e to the kt. Then we could plug in our other point, 24,100, 5. So be careful. Make sure you make the 5 in for the y and substitute the 24,100 for the t. Sometimes students get those reversed. So k times 24,100. So if we divide off the 10 to solve for k, you would have 1/2 equals e to the 24,100 k. We could natural log both sides. And then you have natural log of 1/2 equals 24,100 k. So k equals natural log of 1/2 over 24,100. Now, just a side note here, natural log of 1/2, according to the quotient property, we could rewrite that as natural log of 1 minus natural log of 2. Natural log of 1 is 0. So you would just have natural log of 2. Also, another thing is sometimes the half-life formula for K is written as negative natural log of 2, which is what we have right here, because natural log of 1/2 is the same as negative natural log of 2, divided by h, which is the half-life. Notice when we solve for K, we ended up getting all the way down to 24,100. And the reason where the half comes in, it's always going to be a half if you're dealing with half-life, because the half-life is how long it takes for half of it to remain. So whenever if you know the value c and you divide it, you're going to get a half no matter what. All right. And then the 24,100 is the value we plugged in for t for the half-life. So that's always going to be the time of the half-life. So this formula, negative natural log 2 over h, is just a general formula for getting the half-life without having to do all of this work. So sometimes that is helpful. Okay, so that makes our equation y equals 10e to the negative natural log of 2 over 24,100 t. Now the question asks, how long will it take for 10 grams to decay to 1 gram? Well, we would substitute 1 into this equation. So we'd have 1 equals 10 e to the negative natural log 2 over 24,100 t. And then we could slap that into Desmos and solve the equation there. Okay, so what I did here is I graphed our equation that models the radioactive decay, and I graphed what we want it to equal to 1. Notice the initial amount is 10 up here in green. We want it to equal 1. Now, think about this. We want to solve for the intersection point. The problem is it takes 24,100 years for this to decrease down to 5. We want it to decrease all the way down to 1. So what I'm going to do is adjust the x-axis to go out to like 100,000. And then we could see the intersection point, okay, because we were so zoomed in. We were over a 10 by 10 viewing window. So if we zoom in here, we could get a more accurate solution to our equation right here. So the answer would be approximately 80,059 years if we rounded to the nearest year for this one. Now, you may not have realized it, but in the last two examples, we knew the initial amount. And it's a lot easier to solve an exponential growth or decay problem when you have the initial amount. But that's not always going to be the case. So we're going to look at what to do when you don't have the initial value of y when t is 0. So an experimental population of fruit flies increases according to the law of exponential growth. So we know it increases and it's exponential growth. So it's y equals ce to the kt. And k is going to be positive. After the second, there were 100 flies after the second day, so 2, 100, and 300 flies after the fourth day, so 4, 300. How many flies were in the original population, that's what we want to know. Well, we could plug in both those points. So we know that 100 equals CE to the 2K, and we know that 300 is going to equal CE to the 4K. All right. So in both of these situations, we could solve for either K or T and then set them equal to each other. So for example, if I set this equal to C, so that you would have 100 over e to the 2K, and this one would be C equals 300 over e to the 4K. Now, since they're both equal to C, I can set them equal to each other. All right, so 100 over e to the 2K equals 300 over e to the 4K. Now I'm going to cross multiply. I'm going to multiply the e to the 4K here and then divide the 100 here. So I'd have e to the 4K over e to the 2K equals 300 over 100, or 3. Now remember, if you have a to the x over a to the y, that's going to be equal a to the x minus y. In other words, when you divide like bases, you subtract the exponents. So that's e to the 2k, because 4k minus 2k is 2k, equals 3. We can natural log both sides, and then you would have 2k equals natural log 3. So k is natural log 3 over 2. That's our value of k. Now, it's really simple at this step to solve for c because we already have our equations solved for c here. We don't have to do both of them. We could do one or the other. So if k is natural log 3 over 2, and we put it into this equation, that would give us 300 over e to the 4 times natural log of 3 over 2. Okay, that equals c. So this is going to be 300 over e to the 2 natural log 3. And remember the power property for logs, that 2 in front can go up on the top of the 3 as an exponent. So it'd be 3 squared, which is 9. And then the e and the natural log cancel, and you have 300 over 9, or 100 over 3. Or you could think of that as approximately 33 or 33.3 repeating. So now we have our equation, y equals 100 thirds e to the natural log of 3 over 2t. That would be our equation. And now we know the initial population had approximately 33 flies, just to get back to answering the original question. Okie doke. All right, next one. Example 5, 4 months after it stops advertising, a manufacturing company notices that its sales have dropped. Okay, so we're talking about decrease from 100,000 to 80,000 units per month. Sales follow an exponential pattern of decline. What will the sales be after another 2 months if this pattern of decline continues? So we know it's going to be y equals CE to the KT, and also K is going to be less than 0 because it's declining. So if it drops from 100,000 units per month, that's our initial amount. That's going to be C. We know that we would have 100,000 e to the KT. So if we have 100,000 units per month to 80,000 units per month, and it took 4 months, we know that 80,000 would equal 100,000 e to the 4K. All right, if we divide that off, you would have 80,000 over 10,000, which is 8 over 10, or 4/5, or 0.8 equals e to the 4K. If we natural log both sides, you would have natural log of 0.8, which, by the way, since the value in the natural log is less than 1, natural log of 0.8 is going to be less than 0, equals 4K. So K is natural log of 0.8 over 4. So that's approximately negative 0.0558. Okay, so now we have our equation. Y equals 100,000 e to the negative 0.0558 t. Now, after another 2 months, you have to be careful. We're not going to plug 2 in there because this equation models the sales X T number of months after it stopped advertising. Well, we already know we're 4 months out, so another 2 months would be 6 months. So Y equals 100,000 e to the negative 0.0558 times 6 for that one. And what we would get is approximately 71,500 would be its sales there. And here's just a graph of the situation for us there. All right, now one last thing before we wrap it up. This problem is going to involve separation of variables. It's called Newton's law of cooling. Now, it doesn't follow the exponential growth and decay model exactly, but it states that the rate of change of a temperature of an object, so dy dt, is proportional to, so equals some number times, the difference between the object's temperature and the temperature of the surrounding medium. So that would be the object's temperature minus the temperature of the surrounding medium. So we'll call that S. So it's kind of like exponential growth and decay, but not exactly. So here's the situation we're going to look at. Sam left his cell phone out in the sun on a hot day and it reached a temperature of 100 degrees. He was worried it was too hot, so he brought it inside where the temperature was a cool 60 degrees. They like their house cold in the summer. So after 10 minutes, the temperature decreased to 80 degrees. So we could start with the differential equation dy dt equals some number K times the temperature of of the object Y. I accidentally put a T up here. This should be Y, which represents the temperature. That's why I did that. Minus 60, because that's the temperature of the surrounding medium. So I could use separation of variables here. So you would have dy over Y minus 60 equals K dt. Slap on your integral symbols, and you'd have natural log absolute value y minus 60 equals kt plus c. Now, because the value of y is going to be greater than 60, because the y is the temperature, the current temperature of the object, and it's going to be greater than 60. So we don't actually need the absolute values on there. So we can write that as natural log y minus 60 equals kt plus c. And then we can exponentiate both sides. And when we do that, we would get y minus 60 equals e to the kt plus c. And remember what we said previously about adding in the exponent. So we can rewrite this as y minus 60 equals c e to the kt. And then y equals 60 plus c e to the kt. Now, I know that when t is 0, when he took it out of the sun, it was 100 degrees. Okay, so I can set that 100 equals 60 plus c e to the 0k. So that means e to the 0 times k is just going to be 1 times the c. So you're going to end up with 40 equals c. So I'm going to rewrite my equation. Y equals 60 plus 40 e to the kt. Now I know from the problem that after 10 minutes, the phone cooled to 90 degrees. So if I plug in 90 for y, 60 plus 40 e to the, what was it, 10 minutes? Yeah, 10 minutes, so 10k. So subtract 60, you would get 30 from the 90. Divide by 40, you would get 3/4 or 0.75 equals e to the 10k. Natural log both sides. So natural log of 3/4 equals 10k. So k equals natural log of 3/4 over 10. 3/4 is less than 1, so natural log of 3/4 is going to be less than 0. Now I know my equation. Y equals 60 plus 40 e to the natural log of 3/4 over 10 t. The question asks, how much longer will it take for the temperature to decrease to 80 degrees? Well, we would set 80 equal to 60 plus 40 e to the natural log of 3/4 over 10 times t, because that's actually what we're going to solve for here. Now, if we solve this down, we could use Desmos like we did, or solve for t, solving the equation algebraically. You would get t is approximately equal to 24.09. Now, the question asks how much longer, so it was already 10 minutes when the phone was down to 90 degrees. So if we subtract 10 off of that, you would get about 14.09 minutes. Okie doke. So that wraps up our section here. We have our graph of the situation here. Hope that was helpful to you guys. Reach out if you have any questions, and take care.